Hello, my name is Minkyu Choi. I'm a PhD student advised by Dr. Chinchali at UT Austin. I'd like to thank you all for attending my presentation today. I'm very excited to share my recent work titled Towards Neuro-Symbolic Video Understanding. We have seen a massive surge in video data production, which is having a profound impact on our lives. For example, YouTube generates 500 hours of video every minute, and around 500 petabytes of security footage are produced every day. Lastly, autonomous vehicle generates roughly 10 terabytes of video data daily. The computer vision technology can provide some level of perception. However, we still lack efficient way to process this vast amount of video data and extract meaningful scene when we have complex queries such as find me all scenes where event A happened, event B did not occur, and event C occurs hour later. This is what motivated us to pursue this work. We have seen that video foundation models fail at event recognition when event is rare or logically complex. Even those foundation models from big tech companies surprisingly fail. Let's take a look at the plot on the left. The x-axis is the complexity or reality of the event, and y-axis is the accuracy. Blue plot is based on Meta's Llama model adapted to video, and you can see that it gracefully degrades. It tells us that anything based on this pure deep learning is going to spectacularly fail on this task. Our hypothesis is that it is because semantics and reasoning are coupled in a single network. It mixes everything into one giant network, figuring out what's in every scene and reasoning across time. It's too much into one giant network. What we aim to do is not compete directly with big tech companies and model. Instead, we leverage their advancements in build the best detector for individual frames. However, detecting object in a single frame isn't enough. To truly understand the evolution of events across space and time, especially over extended periods, we need something more powerful since deep learning alone falls short for this level of complexity. What we propose is a symbolic approach based on formal specifications. This approach will allow us to decouple perception and reasoning, one handling the semantics and the other handling the reasoning and understanding. In our work, we propose two formal representations for the reasoning and understanding. We first construct a video automaton, which is a formal probabilistic state machine. For example, let's say we have a video and a set of proposition as known as object of interest, which are dog and cat. In each frame, we have a probability of detection from the calibrated object detection model. In this case, we have a probability of dog in the frame 40% and cat in the frame is 60%. With this probability, we can construct a video automaton as the model of the video, which evolves over time. The second formal representation is a temporal logic specification. Temporal logic specification is an expressive formal representation of system behavior focusing on the timing and sequence of events over time. The complexer query example earlier can be expressed as a metric temporal logic as below. Now we have a temporal logic and video automaton. With these two formal representations, we can formally verify the automaton on the given temporal logic specification, whether to see it's satisfied or not satisfied, or we can even get the probability of satisfaction. Let's dive into the methodology with the example. Let's say we want to find the iconic scene called I'm Flying from the movie Titanic. First, we can construct the temporal logic specification that describes I'm Flying scene, which is always ship on the sea, until man hugging woman, until kiss. The specification consists of three atomic propositions: man hugging woman, ship on the sea, and kiss. Now, given the movie, we can run computer vision perception model to identify atomic propositions. Once we have detection result, we first validate the frame based on the detection since we are only interested in the frame which contains these three atomic propositions. However, this is not enough. Consider if our specification has negation operation. such as event A until not event B. This frame validation function shouldn't be included into our scenes of interest. Therefore, we add symbolic verification to this step, which validates the atomic proposition based on the temporal and logical symbol. So, given frames which pass the frame and symbolic validation, we construct the video automaton, which is a form of Markov chain with probabilities. Finally, we can check this automaton against the temporal logic specification every time a new state, as known as a valid frame, is added to the video automaton. Once it's checked, all frames in the automaton are our scenes of interest, which in this case I'm flying scene. Let's take a look at the demonstration. In this demonstration, our specification is car and truck until bus. So when car and truck are detected, it will be added to our video automaton and it will keep monitor for car and truck and bus from the frame. And when bus is finally detected, it means that our video automaton is satisfied on our temporal logic specification. Video foundation models are insufficient for long-term temporal reasoning. Therefore, we design baselines where we can pass per frame annotations to large language model like GPT-4. While our performance is stable regardless of the length of video, GPT-4 decreased its performance after 1,000 seconds of video, and GPT 3.5 decreased its performance even before 500 seconds. We also evaluated our method on varying event complexity. The benchmark method shows reasonable performance on simple event complexity. However, when event complexity increases, their performance decreases. However, our method shows that stable performance regardless of varying event complexity. In our work, we provide a new dataset called temporal logic video dataset, which we annotate temporal logic specification along with the scenes of interest. In TLV dataset, there are two types of dataset. One is the synthetic TLV dataset, which use well-known image dataset from COCO and ImageNet. Since we wanted to evaluate our method on the real scenario, we offer real TLV dataset, which we annotate temporal logic specification and ground truth label based on new scenes and Waymo dataset. This is the end of my presentation. Please find our work from the QR code below and let me know if you have any question. Thank you.